After looking at Rolle's theorem, we are now ready to look at the mean value theorem, which states, let f be a function that is continuous on a closed interval and differentiable on the corresponding open interval. So starting out similarly to Rolle's theorem, but we don't have the requirement that f of b equals f of a. So we don't need the function values to be the same on the endpoints. We just are looking for a function that's continuous and differentiable, all right? If we have that function, then there is a number c in between a and b such that f prime of c is equal to f of b minus f of a over b minus a. And we can multiply both sides by b minus a to get an equivalent statement. F of b minus f of a is equal to f prime of c times b minus a. Now, what does this even mean? There's a lot going on here. Let me show you a diagram. Okay, here we have two graphs of functions that are continuous on the closed interval from a to b, and that are differentiable on the open interval from a to b. These are smooth curves. At least I've tried my best to draw smooth curves. And so what this theorem says is there is some number c in between a and b such that the derivative of c is equal to this whole thing, f of b minus f of a over b minus a. We have seen this quantity before. F of b minus f of a is rise, right? It's the difference in height between those points. And b minus a is the run. And we know that rise over run is slope. So what this means is that we have a point on the graph where the derivative is equal to the slope of the line segment between those two endpoints. So that means the derivative is equal to that slope, but the derivative is the same as the slope of the tangent line. So this says that somewhere in here, we're going to have a tangent line that is parallel to the secant line between those points. Another way of thinking about this, remember that the derivative is the instantaneous rate of change, and the slope of the secant line is the average rate of change over time. So this is saying there is some number in the interval where the instantaneous rate of change is equal to the average rate of change over that interval. We can look at the second graph as well. If we look at that secant line, there's actually 2 points here where the slopes of the tangent lines are equal to the slopes of the secant lines. We've got parallel lines there. And so we can call these C1 and C2 if we want. And then for the first one, we'll just call that C. And so these are 2 points on the graph where the instantaneous rate of change is equal to the average rate of change over that interval. And what this theorem does is it says if we have a function that is continuous and differentiable on these intervals, the theorem will then guarantee that there is at least 1 point in between those two where the slope of the tangent line is equal to the slope of that secant line, or where the instantaneous rate of change is equal to the average rate of change, or where the derivative is equal to the average rate of change. All of those statements are equivalent to each other. Now, if you're wondering what this actually means, like if there's a real world example, one real world example is if we were driving our car and we had, let's say you're driving your car, over the course of, several hours or something like that. You're going on the freeway, and let's assume that your position function as a function of time is continuous and differentiable. Now, of course, it's going to be continuous. If your position function wasn't continuous, that would mean that you instantaneously warped between two different locations. So we know that that's going to be continuous if you're driving your car in a freeway, and you're looking at where you are on that freeway as a function of time. Now, we also want it to be continuous, so you're not doing crazy things where you're suddenly speeding up at ridiculous rates, or you're getting into a car crash and very quickly slowing down. I know I'm kind of giving something that's hand-wavy, but let's just assume that these conditions are met, and the function that we're dealing with is your position function along a highway over time. Well, we know that the average rate of change is your speed, your average speed over the course of that interval. If you wanted to know your average speed, you would take the total distance that you went, and then divide that by the amount of time, right? The distance would be the rise, the time would be the run, and that would give you your average speed over the course of the 8 hours you were driving, or however long you're driving. And what this theorem says is, if your average speed, for example, is 75 miles per hour, then there is at least one moment in that trip where you have gone 75 miles per hour, right? It's probably not true that you were going 75 the whole time. It's probably true that you were speeding up sometimes and slowing down, depending on if there were a lot of curves or hills. But this theorem says, again, so long as our function is continuous and differentiable, that there is a moment where you have achieved that speed. And this is an interesting theorem for that specific application, because what it means is if you have had a photo taken of your car when you got on the freeway, and then you have your photo taken of your car when you get off the freeway, and they look at your license plates and everything, and they see that your average speed was something like 90 miles an hour, so you know over the speed limit. They don't have video of you going 90 miles an hour at any moment. They just know that over the course of that interval, your average speed was 90. This theorem guarantees that there was at least one moment where you were driving 90 miles an hour. And so this theorem would allow someone who didn't have video of you driving and didn't have a speed gun clocking your speed at any point, but they had the photos of you getting on the freeway and off the freeway, that would be enough to prove that at some point you were going 90 miles an hour, which is over the speed limit. So, pretty interesting. I want to look at one example where we find the value of C, similarly to what we did with Rolle's theorem. So let's look at an example. Let's consider f of x equals x cubed minus x on the interval from 0 to 2. This function is continuous and differentiable everywhere because it's a polynomial function. So we know that it satisfies the conditions of the mean value theorem. And so the mean values theorem says there is a number c in this interval from 0 to 2 such that the derivative of the function at c is equal to f of 2 minus f of 0 over 2 minus 0. So let's write that out. The mean value theorem says that there exists a c in the open interval from 0 to 2 such that f prime of c is equal to f of b minus f of a over b minus a. Well, let's find that value. First of all, we know the function, so we can differentiate the function. The derivative of x cubed minus x is 3x squared minus 1. But because we're evaluating this at c, it's going to be 3c squared minus 1. And that is going to equal to f of b, while our function, x cubed minus x, if we want to evaluate that at b, which is 2, That's going to be 2 cubed minus 2, so that's 8 minus 2, which is 6, minus the function value at 0 is just going to be 0. And then that's all over 2 minus 0. So that's the same as 6 over 2, which is 3. So to find c, we have to solve 3c squared minus 1 equals 3. Now, to get c squared alone, we add 1 to both sides first. So 3c squared is 4. Divide by 3, c squared is 4/3. And then to solve for c, we take the square root of both sides. Now, we know when we take the square root of both sides, we need a plus or minus. And then the square root of 4 is 2. The square root of 3 is root 3. So there are 2 potential values of c, but remember, our interval is from 0 to 2, so that means we need c to be positive. So really, the actual value here is positive 2 over root 3. If you don't want that root in the denominator, if you want to rationalize the denominator, you can multiply the top and bottom by root 3. We could also write this as 2 root 3 over 3. And that is approximately equal to 1.1547 if we want an approximation. And so that is the value in this interval. There's only one, there could have been more, where the derivative at that number is equal to the average rate of change over that interval. So that is our value of c for the mean value theorem.